Okay, good morning, everyone. So for this module, we are going to have problem sets. Good morning. And no quiz. So I've already given the groupings in the GC. That means the problem set will be submitted as a group. But you have to submit it still individually in Google Classroom so that I can return it to you. But you will all each member of the group will receive the same mark. Okay, I hope that's understood. And you will be working as one. That means you will be setting up meetings of your own, and each of you should contribute to the list or the set of exercises I gave for the problem set. And okay, I won't be discussing the applications on business and economics since this is only the only requirement here is problem set. So that means I will leave the thinking or the study of those topics to you. In particular, we call this future value and consumers and producers surplus. So, but anyway, I will be available for consultation in case there are problems with those topics or things you don't or cannot understand. That means today I will only be discussing areas between curves and integration by parts. Okay. And what else? I've already given the quizzes. So I see that some got low scores. So I want you to make up for that and try to do your best and get a high score in our next quiz for module 4. But since this is graded as a group for module 3, so I hope that will help raise your grade up. Okay. So let's start with the example there. And I hope you have read the material I gave 1 week in advance on module 3. Now, I expect since this is a combination of synchronous and asynchronous sessions that you read the material beforehand. That is, you're given Tuesday, 1 day to study the material before Wednesday's discussion. Actually, you have 2 days starting Monday and Tuesday and then Wednesday morning after the quiz on every Monday. So what I will be doing are just examples, no discussion of the technicalities or the theorems and their proofs behind the method or methods we will be using for the discussion today. So let's start. Find the area of the region bounded by the lines. Okay, there are actually 4 lines given there in the problem. 2 are slanted lines. They have a non-zero slope or slopes. Y equals x plus 4. Slope is 1. Y equals 3 minus 1 half x. Slope is negative 1 half. And then the vertical lines x equals 1 and x equals 4. Now, I will leave the drawing of the figure to you. You should still know how to draw lines. One way would be to do point by point plotting. 2 points are enough. Another way would be to get the x and y intercepts and then just connect the points that you have. So I've just pasted the figure here. So you see there in the figure there, the line f of x equals x plus 4, the blue one, which is the higher line, on the region bounded. Okay, that is on the interval from 1 to 4. The lower line would be g of x equals 3 minus x over 2, the orange line. And we want to find the area of that region. Again, bounded by x equals 1 and x equals 4. Between the two lines, x plus 4 and 3 minus x over 2. And if you've studied the material, you know how to get the area. You will be subtracting the higher curve or the lower curve from the higher curve. So our computation will go as follows. We have the area, okay, equal to integral from 1 to 4. Since x goes from 1 to 4. So those will be the lower and upper limits. And then you subtract the higher curve minus the lower curve. So you will have higher curve is x plus 4 minus lower curve, which is 3 minus x over 2 with respect to x. And that's it. All you have to do is set up this integral, and then the rest would be just to evaluate the integral, the definite integral. And we have learned that in the previous module. So proceeding, okay, we will have integral from 1 to 4. If you simplify this expression here, you will be getting 3 halves x plus 1. A minus and a minus, so the other one becomes positive. So you'll get 3 over 2x, then 4 minus 3. And this is easy. You will just be using the power rule. So for this one, you integrate it, you'll get 3/4 x squared. And then plus x for the integral of 1. And then limits 1 to 4. And then you've learned this again in the previous module. So you'll be substituting 4 first, then substituting 1, and be subtracting and verify, okay, that you will be getting 57 over 4 square units. This is the area of that region. So in other words, just the setup that's new here. Once you've set up, all you do is evaluate the definite integral, and that's it. You get the area. For the setup, again, it's higher curve minus lower curve. And then the lower and upper limits will be determined by the smallest possible value of x in the region, and then highest possible value of x in the region. That is, they are 1 and 4. Now, of course, this could have been gotten by using the formula for the area of a trapezoid, because the region is trapezoidal. And to get the base, that would be easy. You just get the y values at x equals 4 and at x equals 1, and you subtract the y values to get the bases of the bases of the trapezoid. And the formula for the area of the a trapezoid is base 1 plus base 2, and then height will be just 3, okay, divided by 2. Of course, that won't be our concern here. But that can only be done if the region is a polygon in general. But if it's not a polygon, if the region has a curved boundary, then definitely we will be needing integral calculus to get the area of that region, as in the next example here. Okay. So this time, there are no x values or x boundaries given. So that means this might, of course, it should be a closed curve. the two curves will in fact have an intersection, and the area enclosed by the two curves will be the area we will be looking for here. Now the functions are f of x equals 9 minus 1/4 x squared, it's a parabola, and g of x equals 6 minus x, a line. And here's the figure. Now, if you look at the figure, the parabola opens downwards. Obviously, that should be so because of the negative coefficient of x squared. And the line has a negative slope, so it should go downward. And there are points of intersection. Now, before I show you how to get the points of intersection, I will just be computing first the area, giving you right away what those points are. So actually, the points of intersection will be at x, okay, equals -2 here. This should be -2. And the other point of intersection is at x equals 6. Now, it's easy once you have the points of intersection. All you have to do is set up the integral. So given that those are the points of intersection, let's proceed. So how do we set up higher curve minus lower curve? What are the lower and upper limits? Note that the x values will range from -2 to +6. -2 is the smallest x coordinate in that region, and 6 is the highest y coordinate in that region. So the integral will look like this. The area of the region is given by the integral from -2 to 6. And the higher curve in that interval from -2 to 6 is always the parabola, whose equation is given by 9 minus 1/4 x squared. Minus the lower curve, which is always the line 6 minus x, and then that's it. You have the definite integral set up. That gives you the area. The rest is computation. So just showing you the computation, we will have the following. Once simplified, the expression inside becomes 3 plus x minus 1/4 x squared. And you integrate, you'll be getting 3x plus x squared over 2 minus 1 over 12x cubed. And then plug in the limits. 6 first, then -2 subtract. And your final answer should be 64 over 3 square units. So I hope I don't have to show the substitution here. So that will be calculator work. Of course, you have to be extra careful. You might make a mistake along the way. And that's all that you need to do. Set up the definite integral. Higher curve minus lower curve. Determine the lower and upper limits. And how do you determine the upper and lower limits? You need the points of intersection. So the thing now here is to just show you how I got the points of intersection. This is from pre-calculus. You simply solve the system arising from the equations of the two curves. So what are the equations? Let's show here. This is the system you have to solve. The equation of the parabola is 9 minus 1/4 x squared. And the equation of the line is y equals 6 minus x. So this is easy. We just equate the two. 9 minus 1/4 x squared equals 6 minus x. And this will become quadratic. Now, if you multiply by 4, okay, to get rid of the fractions and rearrange, you will be getting x squared minus, Okay, let me show you the next step. You will get, okay, let's multiply by 4 both sides. So you'll get this 36 minus x squared equals 24 minus 4x. And then you rearrange and factor out the constant 4. You'll get this x squared minus 4x. Oh, sorry, no need to factor out the constant. So you'll get this. Okay, just rearrange, transpose everything to the right hand side, and the other side will become 0. Then I just switch the sides. And then this can be solved either by the quadratic formula or by factorization. Turns out to be factorable. So we do that, we get this factoring weighted to 0. So you get the points of intersection, -2 and 6. Note that the y coordinates of the points of intersection are not needed in this problem because we only need the lower limit for x and the upper limit for x. So this will be the lower and upper limits, -2 to 6. So is there any question? Okay. So it's not always the case that one curve will be the higher. Okay, always on the entire interval as shown in the next example there, where we are to find the area between the sine and cosine curves over the interval from 0 to pi. At least we now have the lower limit and upper limit. So how do we set up the definite integral that will give us the area of that shaded region? So it's the area between the sine curve, the orange one, and the cosine curve, the blue one, and from 0 to pi. So those will be the vertical lines, x equals 0, x equals pi, and the enclosed region between those lines and the curves. So over one part, in one part, the blue curve is higher. On another part, the orange curve will be higher. So that means we have to be careful with the setup since it's the higher curve minus the lower curve, and it will depend on the interval now. So that means that we still need to find the point of intersection of the two curves there, the sine curve and the cosine curve. And in calculus, in trigonometry, we know that one of the points of intersection of the sine and cosine curve is at pi over 4. And we get that from the fact that 45 degrees has the same sine and cosine. Square root of 2 over 2. You still recall the unit radius there, and then the x and y coordinates will be 1 over square root of 2, 1 over square root of 2. Cosine is the x coordinate, and they are equal. And there are others, of course, but we are only interested in that region there, the interval from 0 to pi. Okay? So let's set up the integral. So we have to split it into two. The first region is from 0 to pi over 4, this region here. And the setup will go as follows. We have integral. So the first region will have an area given by this integral from 0 to pi over 4. Blue minus orange. So we have cosine x minus sine x. And then plus the second region, it will be from pi over 4, lower limit, and the pi. pi, and it's sine minus cosine. So that will give us the area. We have to just evaluate each integral and add and verify that you should get to square root of 2. I won't be showing the details of the calculation. The more important thing in this discussion is how to set up the definite integral that will give us the exact area of the region we are looking for. You can use your calculator anyway to arrive at that same value, or you can give the exact value of 2 square root of 2, knowing that sine and cosine pi over 4 is square root of 2 over 2. Is there any question? Now, there are two problems in the problem set, okay, that is on this topic, area between curves, I think only two. So you are not sure if you have to split the region or there's just one curve that's always higher than the other curve. So let's proceed to the next topic, integration by parts, unless there's a question still on the previous example. I believe there's none. Okay, so integration by parts, from the word itself, we know that this requires dividing the task into several subtasks, which will make us, or one of the tasks, of the two tasks, easier to integrate than the original integral given. Now, there's no way we can find this using the technique of substitution. Remember when I gave an exercise on that, we found that ln u du was a dead end because we don't have a formula for that. Now, we will show later how to get the integral of ln x using this technique. So let's illustrate it first for that example. Integral of x sine x. So the formula you should have read by now, and you should have understood why it is so. It is the inverse of the formula of, or the product formula, remember, for differentiation. If we undo the product formula, which I have written in the module, if you want to ask me why that is so, okay, you can consult me. Otherwise, okay, you can just follow me as I use it to evaluate that integral. So this is the formula for integration by parts. Now, this is what we want to evaluate. That a key here is to set it up so that this one will be easier to evaluate. So with the proper choice or choices of u and dv in this integral, we might get something like this that's very easy to integrate, almost directly. Okay? So how do we do that? It depends on the choice, but the proper choice of u and dv here will be the following. U will be set equal to x. This is u, and then the rest will be dv. So dv will be the rest. That includes the dx. So it's sine x dx. So we have du. If we differentiate, we get du equals dx. And then if we integrate, we'll be integrating here because we have a derivative. So here we differentiate, but here we integrate. So integrating gives us v equals integral of sine x is negative cosine x. So we apply the formula. U dv will be our integral. Okay, u dv. And then uv will be negative x cosine x, no integral involved there. and then minus v du. So that will be negative minus integral of negative cosine x dx, which will become positive. And you know the integral of cosine. It is positive sign. Okay, so, and then you have negative, negative, positive. So our answer will be negative x cosine x plus sine x plus the constant of integration. You can check, try to differentiate the answer, you will be getting the integrand here. Are there any questions? Okay, none. So let's proceed to the next. Let's evaluate the integral of ln x dx. So this can be done using integration by parts, but not by substitution. And obvious substitution, or sorry, choice of u and dv here will be this. U equals ln x, dv equals dx. So differentiating u, you get here du equals 1 over x, then dx. Integrating v, we have v equals x. We omit the constant of integration, by the way. We just need one particular antiderivative. So omit the c. So v equals x. And then we set up again. Okay, so we have u dv, the original integral, equals uv, just multiply, minus v du, which becomes 1, which makes it an integrable. Okay, the word integrable means we can integrate it using the ordinary tools of calculus. So that's just 1. Okay, and the integral of 1 is x. So x ln x minus x plus c, and you can check. If you differentiate this, you'll get ln x. Actually, that was shown in differential calculus. So next. Now here, you will be using integration by parts twice. So let's show the integration. So for this one, okay, you can try this combination first. Okay. Now, if you differentiate, you'll get 2x dx. And then v, integral of cosine is sine x. Omit the c. And then the integral becomes uv. So you have x squared sine x. And then minus v du. So that will be 2x sine x dx. Okay, if you notice, this is what we've done in the first example. This one here. Now, if we haven't done that, we would have to do it again one more time by parts. So if we do that, we will be getting this answer. So I will just be substituting that into this one here. So we'll get the answer as x squared sine x minus 2 times the answer in example 1, negative x cosine x plus sine x. And then we'll just put the constant outside in the final. So answer is x squared sine x plus 2x cosine x minus 2 sine x plus c. Now, of course, we skipped this because we've already done it. But really, we did integration by parts twice. So that's integration by parts. There are two, I think, or three problems on integration by parts in the problem set. Okay, some applications, and that's it for today. I won't be, as I've said, discussing the application specific to business and economics, future value, and then consumers, producers, surplus. Now, I will just be doing three for today, and then we will just have appointment, okay, if you need to consult with me. We won't have a live consultation since this is just problem set. Now, in differential calculus, you know that the derivative of the distance is the speed or the velocity. Now that we know how to undo differentiation, if we know how fast a car is going, we can calculate the distance it covers in a given time interval. So let's have the problem there. Okay, the velocity of a car is given by that formula, v of t equals 0.4t. It is measured in meters per second. So if you plug in a particular value for time, you'll get the instantaneous speed at that time. So in 1 second, at t equals 1, its speed is 0.4 meters per second. So its speed is varying. In fact, it's increasing. So we want to know how far the car has traveled after 60 seconds. So we know that the distance is the antiderivative of velocity, as velocity is the derivative of the distance with respect to time. So that means we just integrate velocity and we get distance. So we will get the distance traveled after 1 minute, and that will be the time period from 0, time equals 0 to time equals 60, since it is in seconds. So do not substitute 1. Okay, 1 minute is 60 seconds. So integrate, and that's it. Set up the integral, and then evaluate this integral, and you get the answer of 720 meters. Okay? So that's actually just the fundamental theorem of calculus. We use the fact that the derivative and antiderivative are inverse processes. And so with other types of problems where the rate of change of a given quantity is given, like in this one, this is actually on business, total income, and we are given in the problem the rate of change of the income, or what we call in business income flow. It's f of t. And f of t gives us how fast income is coming in, or perhaps going out if, although technically it's income, we do not have a negative income, but surely f there is positive because e is always positive, the exponential function. So if you plug in, let's say, a particular value for time, you get how fast the income is coming in or flowing at that particular time. So the question is, if we know how fast the income is changing or coming in, how do we get the total income in a given time period? So let's answer the problem there. So again, the derivative and the antiderivative are inverse processes. We are given the derivative here. It's rate of change. Okay, it's not the income, it's the rate of change of the income. So we integrate, and we want it in 3 days. Actually, the lesson plan I gave, or the lecture note I gave, module 3, has an error. It's the same problem, but my integration was wrong. So I'll just make the corrections here. So we integrate 3 days. So pesos per day. So that means we integrate from 0 to 3. By the way, it's not always from 0. The question could be like, okay, from day 5 to day 10, then that would be 5 to 10. But here, since it's just the first 3 days, so the lower limit will be understood to be 0. So 0 to 3, then this is the rate of change. And then we integrate the rate of change with respect to time, of course. And if you integrate this using substitution, you will be eventually not multiplying. In differentiating it, you'll be multiplying by 0.05, but in integrating it, you will be dividing by 0.05. And just verify that you have 1,294.67 pesos. This will be his income for 3 days. If the currency is not given, just put their units of currency. And last example for today, unless there's a question. So anyway, this is recorded, so you will be able to view it again and pause those parts where you think you need to verify the calculations. And then we'll end. So no question still. Let's have the last one. So here, what are we given? Rate of change of what? WT, what is it? We are given the symbol W prime of T. So it's the rate of change of W of T, where W is the growth, or say the population of the yeast culture. But since it's measured in grams, not in the number of bacteria, so we just call it growth. So the rate of change of growth is given by 0.3 e to the 0.01 t. So to get the growth, the total growth for the first 10 hours, we integrate that from 0 to 10 since it's in grams per hour. So no need to change the unit, okay, or to convert it to another unit. Okay, it's already in grams per hour. So 0 to 10, 0.3 e to the 0.01 t, and that's it. In other words, you are just given always, if you know the rate of change of a quantity, you can calculate the quantity itself by doing anti-differentiation or integration. So integrating this one, you will get 0.3 e to the 0.01 t over 0.01 from 0 to 10, and check, this is about 3.16 grams. So is there any question before we end the session regarding the problem set? When it is to be submitted, I indicated there already, Monday, next Monday, 5 p.m. Again, let me repeat, you have to submit individually your work as a group in Google Classroom, so I can return it to you so you can see your grades for each module. Okay? So I hope you already coordinated with your group mates. So if there's no question, that's it for today.